Hello everybody, I am Claudio from the Astroframe, and today I'm going to show you how to apply the continuum subtraction to your images. In particular, today we're dealing with nebulae. As you can see, I have here two beautiful images of the Horsehead Nebula and the Flame Nebula. And this tutorial can be applied also to big galaxies like M31 and M33. At the moment I'm working on a different tutorial, on different steps on small galaxies like M51, because during the star removal the software will mistake the H-alpha regions, which appears to be round in the small galaxies. For example, the star X and StarNet will consider those H-alpha regions as stars and they will remove them. So I'm just testing a way of protecting those regions, and as soon as the workflow will be ready, I will post a second video just for continuum subtraction on small galaxies. So guys, stay tuned. First of all, I would like to thank all the people of the Discord community of the Seestar collective. This is an amazing community where you can find people of different level of expertise. We gather on many DSOs tons of hours of integration. In this case, on the Horsehead Nebula, we have got 21 hours of integration on the ear cut, and around 92 hours of integration on the light pollution filter image. First of all, let's start about the naming of these images. What's the RCAT and what's the LP image? Basically, it's a way the Seestar names the broadband and the dual band images. A broadband image is an image where light is like all the spectrum of the visible light is captured by your telescope, so you will get images with pretty much pleasant colors, and you will see also the faint nebulosity around your nebulas. Whereas the LP filter image is an image that basically is a dual band image, where only the spectrum of H-alpha, that is to say hydrogen alpha, and O3, oxygen 3, are captured. As you can see, the colors on these two images are quite different. For example, let's take a look at the IC432 region here, and you can see quite a very big difference in the signal, in the red signal, let's call it like this, which is the hydrogen alpha, which is more present, of course, in the dual band image. So what's the continuum subtraction and what is it used for? Because many people don't know about this procedure, and they asked me, why do you use these steps on your two images? Because some people usually stuck together the RCAT and the LP filter images together, but this is a wrong way to combine those two images, because if you stuck together the RCAT image and the LP image, you will alter the color of the stars, and of course you will impact also on the true colors of the of the ear cut image. As you can see here, the flame nebula in the LP image is reddish, whereas in the ear cut image is more of a yellow, which is the true color of this nebula. Some people will also we will see during this tutorial something very interesting about SPCC, because some people like to make this nebulosity behind the Horsehead Nebula of a more of a red color, but this and keeping the flame nebula red yellow, but this is quite wrong, because behind the Horsehead Nebula we don't just have hydrogen alpha, we also have hydrogen beta and hydrogen gamma, and those particular emitting spectrum has different colors, because the hydrogen alpha appears to be red, the hydrogen beta appears to be more of a teal color, and the hydrogen gamma is essentially blue. So the color you will get when you mix all these spectrum together is essentially like pink / magenta. Okay, so what's the first step you are going to use in your continuum subtraction? And the continuum subtraction is very useful. I was telling you before what is it used for. The continuum subtraction lets you extract by subtraction all the H alpha from your LP image, and lets you combine it with the ear cut image. So you will get the pleasant colors of the ear cut image, but you will have a boost on the real H alpha regions on your RCAT. Because if you over process your RCAT image just to show more the H alpha regions, you will get an image that is not at the same level of another image who's undergone the continuum subtraction. So the first step of this process is to star align your image, and this is a very important step, because you need first of all to star align your image, and second of all you need to crop them at the same level of to the same framing level. Just to make this video a little bit shorter, I already star aligned and cropped my image, but you can go to process, all processes, and go to star alignment. Let's reset this. You have to select your reference image. You can choose between the RCAT on the or the LP. I will choose, for example, here just to show you how to do it. You select the RCAT as reference, and you go to here, target images, you click on add views, and you select your LP image. Then you just have to drag and drop this triangle on your LP image, and the software will start align those images together. Then the second step is to crop your images to the same extent. I use the dynamic crop here in PixInsight. How do you crop these two images? How you apply the same crop to these two images? You have to select your reference image, just go for the image where you have less field of view, or where you find much more artifacts at the edges of your image. You have to draw a rectangle. For example, let's draw this rectangle here. I usually select as algorithm the cubic B-spline and toggle gamma correction option. Before applying the crop to your image, you have to drag and drop this triangle on your LP image, and as you can see, the image has been cut. Only after this you can apply the cut to your reference, to your target image. As you can see, the images have the same exact crop. So let's go back, because I liked the field of view of my previous image, and let's go for the DBE, that is to say the dynamic background extraction, which is a very important step, because the continuum subtraction is very sensitive to gradients, so you have to be very careful to remove all the gradients from your image. I usually like to use the DBE, that is to say the dynamic background extraction, because it just gives you more, let's say, more control over the regions you want to correct and you want to remove gradients from. You just click, after opening a dynamic background extraction, you just click on your image, and then you set the tolerance and shadow relaxation. Let's go here. Because I already pre-made a DBE just for the purpose of this video. So you have to put 2.5 as tolerance, shadow relaxation of 6.0. You then have to go on sample generation. I selected a default sample radius of 20 for my image, but you can select another value that may fit better with your own image. Then you click on generate to generate all these little small squares with an X at the center of it. Then you have to go to target image correction, select subtraction as your correction method, and you have to toggle the normalize option. One of the most important things you have to be very careful is to avoid bright stars. For example, here you have to move these square away from this bright star here as well, and you just like select the darker and the fainter regions of your image, because many people don't really understand how to use DBE, and I might do a tutorial just for this very powerful instrument. Let's continue to remove our samples from bright stars. Let's say I will put this square here, I move it here, and then maybe just move these away. Let's see if we are targeting by mistake other bright stars. Maybe I will put this square here, and I think it's good for now. So let's do the DBE, let's apply the DBE, and as you can see, now you have an image that is corrected from gradients. Let's take a look at the gradient, and you can see that the gradients here are quite heavy in some regions of this image. Let's close the gradient model, that we don't need it, and let's close the dynamic background extraction. So we are going to keep this image here, and let's reduce to icon the original image. For the moment, let's reduce it to icon also the DBE one, and let's work on the LP image. Same thing applies to the LP image. You have to take a look at the gradients you have in your image, and you have to like remove the gradients in a very similar way you did with the ARCAT image. So let's move it here. Okay. Same thing, you have to avoid bright stars. I will put this square here. I will move these here, and this one is not good. Let's put it here. Same applies to this. Okay, and we're done. Let's run the DBE also on this image. Let's close the window. Okay, let's auto stretch the image. You might see sometimes quite weird colors with posterization in your image. You did nothing wrong. You just have to activate the 24-bit lookup tables just to see a smoother image. As you can see, now the image looks a lot better. Let's take a look at the background model. Let's turn on the 24-bit visual, and as you can see also here, there were a lot of gradients in our image. So let's discard the background model. Okay, I will reduce to icon also my original LP image, and now let's work on the DBE one. The second or the third step of this tutorial is to make a spectrophotometric color calibration, because your images must be color calibrated. I think that I have to run first the image solve, because after you cut your image, you will lose your astrometry. So you have to image solve again. Let's wait a little bit. For the SPCC, I'm using the Gaia DR3 databases. Okay. So this image, okay, is done. Then let's color correct it. For ear cut image, for the ear cut images, I personally leave the Sony color sensor UV ear cut, just the standard values. You can choose a region of interest in your image. Sometimes it helps you like getting a better color calibration. Other times it will make weird colors appear. So you have to try both these like these methods of color calibrating your image. Let's apply the color calibration to the ear cut image, and let's see what will happen. Let's wait a bit. Okay, let's see. And it's done. Now we have to open the screen transfer function. You have to link the RGB channels, and you auto stretch the image. Okay, here we are, guys. Sorry, I had to cut the video because someone rang at my house. So, like after SPCC, you will see the true colors of these beautiful nebula. As I told you before, the true color of this nebula is like a sort of pink, sort of magenta. This is because when you mix a hydrogen alpha, hydrogen beta, and hydrogen gamma, you will get a pink color. And as you can see, the more you move to the fainter regions, the more the color will become more red, because hydrogen alpha is more present in the fainter regions than hydrogen beta and hydrogen gamma. Okay, now that we have color calibrated our ARCAT image, it's time to color calibrate our LP image. For the color calibration of our LP image, I am going to select the Seestar LP R for red filter, Seestar LPG for the green filter, and the Seestar LPB for the blue filter. Again, you can choose your region of interest, or you can leave it like this. So let's drag and drop the triangle on your image. Of course, I have to image solve or also this one. So let's go on image solve. Hopefully it will be faster this time. Okay, and it's done. Now apply SPCC. Let's wait a bit. Okay, and it's done. Let's close this window and let's auto stretch the image. As you can see, you get two different colors, and here without gradients and with the image that is color corrected, you can see better what's the difference between an ARCAT image and an LP filter image. Here on the fainter regions, you can see much more hydrogen alpha that you don't notice, and you can't see on the fainter regions of the ARCAT image. This is because the light pollution will make it difficult, really difficult, if not impossible to see. After you apply the color calibration, let's close the screen transfer function, and we have to remove, of course, our stars. I will use for this tutorial the star exterminator tool, but you can use, if you don't have the RC Astro tools, you can use StarNet 2, which will deliver a pretty much similar result. Let's open star X. I toggle generate star image and large overlap, and I drag and drop the triangle on my image. It'll take a while. Okay, stars have been removed, and the image, as you can see, is lovely, and it's very like surprising how you can get an image like this from a very small smart telescope. Of course, you need a lot of hours of integration, but the image is absolutely stunning. Okay, so I will you have to reduce to icon your ear cut stars, and let's do the same thing to the LP image. Okay, let's wait a bit. Okay, and it's done. Okay, let's close Star Exterminator. You don't really want the LP stars because those stars are just blue and red, so you don't really need this image, so you can discard the LP stars. I will also discard the RCAT stars because I already have like removed them previously for this tutorial, so I will keep these ones. So next step you have to do is to now it comes the difficult part. You have to separate those two images in the single RGB monochromatic channels. So let's temporarily close reduce to icon the LPDBE image, and let's focus on the ERCAT image. So you have to split the image by clicking split RGB channels. Okay, you don't need the blue channel and you don't even need the green channel either. We will just focus on the hydrogen alpha. Maybe in the next tutorials I will show you how to extract also oxygen 3. For the Horsehead Nebula you don't need to extract oxygen 3 because all the blue that you can see here are pretty much reflection nebulae. So you don't really have a lot of O3 in this image, in this nebula. Okay, let's auto stretch the red channel and let's do the same thing to the LP image. Okay, let's discard the blue and the green channel, and let's keep just the red channel. Okay, let's auto stretch the image, and here again you will see some posterization, but you just have to click on the 24-bit view. You have to like make some small corrections on your monochromatic channels. That is to say, you have to apply the noise exterminator, you have to reduce noise on both your images, because when you subtract when you apply continuum subtraction, you will get an image that is noisier. So if you don't apply noise correction here, you will end up with a very noisy image. I would say to use the 0.7 denoise factor. You drag and drop it over your ERCAT image. Let's wait a little bit for it to finish. Okay, guys, sorry again for the interruption, and let's continue our tutorial. Now you can see also here some posterization. Again, click the 24-bit lookup tables. As you can see now, the image is quite smooth and honestly is spectacular. Of course, you can see some artifacts here at the edges of the image, but I think that it's fine. You can just crop them out when your image is ready. Now let's apply the same, and this is very important, the same level of denoise to your LP red channel, just to have two very similar images. Okay, and it's done. Beautiful. Let's close the noise exterminator. A crucial step here that many people don't do is that you have to linear fit your monochromatic red channels. So let's just keep the ear cut image auto stretched, and let's go to process, all processes, and let's open the linear fit. As your reference image, most of times you have to select your LP red channel. So let's go here, click on the view selection, and let's select our LP DBE1 red channel. Okay, and now you just have to drag and drop it over your ear cut image. Okay, and it's pretty much done. Okay, let's see here. Yes. Okay, I was making sure that the steps were again correct for this tutorial. Okay, let's auto stretch the LPDBR, and now you just have to keep, of course you will see some a very strange image, but you have to keep it like this. It's very important for the H-alpha extraction. So after this you go to script, and I use the let's see where it is, here in toolbox, the Continuum Subtraction tool. Here you have to select in the RGB view or red channel view your ear cut DBE red channel, monochromatic channel. As you can see now, you see it, you see a normal image. Okay, then in the narrowband view you have to select your LP DBE image. It seems that the image is pretty much the same. This is because you have to select the amount of extraction you want to apply to your image. For this image, I will go for the maybe 85%. You will see a very strange image, like a very broken image in some way, very, like as I told you before, it's like a very noisy image. There is some clipping. You can also try with a 0.9. Okay, and it seems pretty fine to me. Let's try with 0.9 and let's apply it. You will get an image extremely weird. Again, it's posterized, so you have to click the 24-bit icon. Okay, now that you have your, this is essentially your H-alpha, I will call it H-alpha tutorial for this video. Now you have to combine the monochromatic H-alpha tutorial to your ear cut DBE image. How do you do it? Let's go to script, toolbox, and click on combine HA with RGB. Let's open this tool, and this tool will ask you to, this script will ask you to select your RGB view, which is the ear cut DBE1. Since the image is in linear mode, you have to toggle linear image, and since it's color corrected, you have to link the RGB channels, and then you just select your H-alpha view. In this case, it was the H-alpha tutorial. Let's wait a bit, and as you can see now, the image looks much more better than before. You can also select the amount of H-alpha. Let's see with a double amount of H-alpha what will happen. As you can see, you will get much more red regions. You don't want to overuse these amount too much, because like sometimes, especially on galaxies, here it's not a big deal, to be honest. It will make very strange, very weird artifacts on the arms of the galaxy. I would go maybe with a value. Well, it depends on your own on how much you like these red regions to appear. Let's try different settings. Okay, maybe the IC432 is too much red. Let's go for an amount of maybe 5.5. Okay, sometimes, and we'll see it in the next tutorial, you can also remove H-alpha background noise, because like for nebulas with a lot of fainter nebulosity, you don't see this too much. But with galaxies that have a background that is pretty much dark, when you combine the H-alpha image to your R-cut image, you will get red pixels in the background. So you can raise this like background level here to remove the red pixels from your dark background. You can also apply some convolution for the hydrogen alpha. The convolution, when you combine the hydrogen alpha image to your R-cut image, sometimes, especially in galaxies, you will start to see very sharp edges that you don't usually see on galaxies, because like the H-alpha is not a confined region, but this like emission is fading away in the darker areas, in the surrounding areas. So you can apply also some a little bit of convolution, which like smooths out the H-alpha regions. Here you don't see much difference. Let's go back. No, there isn't a very big difference. I will select 1.5, for example, in this for this image, and you just click apply. Okay, and now you have your ear-cut image combined with the H-alpha from the light pollution filter image. Let's go back to see the difference. Okay, let's go back. As you can see, yeah, a beautiful image, but the combined image is absolutely stunning. So this is how you make the continuum subtractions for the continuum subtraction for nebulas and for big galaxies. I will not go farther than this, because this is not a tutorial for the editing of the Horsehead Nebula. If you're interested in this, I can make a separate tutorial, and I really hope you liked this tutorial. I hope it will help you to achieve beautiful and amazing results, and I'm sure you will get stunning images. And if you like this content, I'd be very happy if you support me by clicking like, maybe subscribe to the channel and share it with your astrophotographer friends. Now, I will, let's say in Italian we say salutare. I will say bye bye and see you on the next tutorial.